This is the screencast of Biweekly Contest 136. Starting in a few seconds, let's see how this goes. Alright, what do we got? Typical Leetcode contest issues happening already, I see. Okay, Q2. This is like the easy version, this is the harder version of the same question. Alright, let's look at this for now. We're given an n by n binary grid. A row or column is considered palindromic if its values read the same forward and backwards. You could flip any number of cells in the grid from 0 to 1 or 1 to 0. Return the minimum number of cells that need to be flipped in order to make either all rows palindromic or columns palindromic. Okay, so we can return columns or rows, right? So I think what we probably want to do here is we want to count the number we need to switch for the columns and then the number for the rows and then whatever's the minimum, right? So here we have 101. This is already a palindrome. This is not a palindrome. So here what we can do is we can change this. So this whole thing's a palindrome. This column's already a palindrome. And then we can switch this. So this is a palindrome, right? We could also, maybe the same thing for the columns, right? We could change this one to a palindrome, this one's a palindrome. So for here, to make this a palindrome, again, it's like this, it's kind of the same. So this is kind of showing cases where it makes both, but that's not actually a requirement, right? We just need to find the minimum. So let's do min rows equals float infinity. Okay, so what we can do is we can do for row in grid, and then we can do for I in length row. What we could do is say first, last, or actually let's do this. Let's do left is 0, right, equals length of row minus 1. We'll do it while left is greater than, or left is less than right. What you can do is if row left does not equal row right, what we could do is say min, let's make this actually 0 to start, and we just increment our counts. So then min rows plus equals 1, else, yeah, so just that case, right? So then we do left plus equals 1, right equals 1. Okay, so then we need to do our columns. So we do, again, for, so I'm trying to think of an efficient way to go through all the columns. So we can do for row index in length of, or maybe we'll do for column index in length of matrix grid 0. So we're going to go through each column, basically, and we'll do top equals 0, bottom equals length of grid minus 1. And then what we can do is while top is less than bottom, we can do the same thing. So if grid call index top does not equal grid call index bottom, we can do min call plus equal 1, and then we'll do top plus equals 1, and bottom equals 1, and we return the min of min rows and min calls. Now what did I do? Length in range. Let's see. Out of range. Top is less than bottom. Right, so our top should be 0. Length of grid minus 1. So why would we not... We're going out of range. Top equals 0. Alright, so we're comparing the top and bottom of that column. Well, top is less than the bottom. Why would that not work? Triangle grid column bottom. Length of grid 0. Oh no, this should be, hold on. This should be top column index, right? Yeah. It should be bottom. So I just got my indices confused. So this is 2, this is 1, 0, 1, 0. Submit. I don't like how it doesn't give you the green or red anymore. It's annoying. Okay, well we got that one. Let's go to the Q1. Let's get that one finished. Find the number of winning players. So we're given an integer n representing the number of players in a game and a 2D array pick, where pick I equals xi, yi. Represent that player x picked a ball of color yi. Player I wins the game if they pick strictly more than I balls of the same color. In other words, player at least 2 balls of the same color. Oh, I see. The number of players who win the game. So they need to pick balls of the same. So basically, we want to count the number of balls they pick up. If they pick strictly more than eyeballs of the same color. So does that mean that they can potentially, can they pick another color, but then as long as they have one color? Okay. Here, I wins the game, right? So what if we do, probably the best way to like, n equals 4. So let's do count. We're going to have an array where each one is a default dict. And we'll do collections import default dict. Let's do this int for I in range n. Right, so basically what I'm thinking is each index will basically represent a player, and we'll just count all their balls separately. So we can do for winning, or rather for player ball in pick. I'm going to do is count player, and then we're going to do ball plus 1. So when I go through the counts, let's have a winners array of this. We do for player ball count in count items, and we can do for key value in ball count items. Say if v greater than player, winners. Let's do this. When equals false. When it's true, and we'll do if win winners and player. Okay, let's run that. Count has no counts. There we go. List has no attribute items. So okay, so this is not items. This was just should be enumerate, right? Because each player is actually the index. Return winners. integer. Length of winners. See, this is why you gotta read, because I'm just coding without really reading what I'm actually supposed to do. So we get 2, 0, 1. I think that's good. Cool. Okay, so let's go to Q3. I'm guessing this is probably similar. Okay, so here, it seems like the difference is we have to make all the rows and all the columns palindromic. So I'm trying to think how we can do this. So basically, if we choose this, we have to make sure, right, that, so say if this here is 1, but this was 0, that means we have to change 2, right? We'd have to say this needs to change, but also one of these needs to change. But it's like, how do we actually determine what's the optimal choice? So constraints are pretty high, so I'm guessing that we, wait, why is this changing all to zeros? Why are we changing this to 0? The total number of ones in grid is divisible by 4. Oh shit, this is tough. Okay. Total number of ones in grid divisible by 4. Okay, so say if we have, I'm just going to draw this example out here, 1, 0, 0, we have 0, 1, 0, and then we have 0, 0, 1, right? So here we have 3, right? So what we'd have to do here is we'd either have to increase this by 1 to 4, or we have to decrease it by 3 to 0, right? So we want to find the minimum way we can do this. So we could technically do this, right? It's saying, like, if we decrease the number of ones to 0, then technically it has to be palindrome, right? So this is valid, right? So if we change all the, if there's no ones in the grid by default, everything has to be 0. So that's a palindrome, right? So that's an option. We can just decrease all the ones to zeros. And that seems like what they're doing in all these cases, right? We are, well, not this case. This case, we're adding a 1, right? Here, we're decreasing all the ones to zeros, and also here. So maybe if, like, if number of ones is closer to like 0, 0 or like lower, so 0 to 4, then to 4 and 8, right? So if it takes less steps to decrease it than to increase it, maybe we should prioritize that. But then the issue is, like, with this, how do we know the optimal way, right? So what if instead we had something like this? What if we had 1, 1, 0, we had 0, 0, 0, and we had 0, 0, 1. Right, so how do we do this here? So what we could do is we could change 1 to 0, so this will become a 0, this becomes a 1, and this becomes a 1, right? So this is also 3. I'm trying to think of another case where it makes, like with this would work. So if we had 1, 1, 1, we had 0, 0, 0, and we had 0, 0, 0. Right, so in this case, what we'd have to do is we'd have to take this 1 here. We can make this a 0. We could make this a 1, or we could make this a 1, right? So we could do this. So this again is 3. And that would be the same as basically changing all these ones to 0. We get the same count. So what if we do more than 4? What if we have 1, 2, 3, and we have 4, 5. So here we have 5 ones. So what can we do? We could either say we need to make this column palindrome, so we could change this to 0 and this to 1. But now this is a palindrome, but this is not, right? So we have to do maybe change this to a 1, and this to a 1, change this to a 1. Right, so we have 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1. This is 1, 2, 3, 4. We change. Is that the most efficient way to do this? I'm not sure. Let's see. There's a different way. So, what if we did this? So we have 1, 0, 1, 0, 1, 0. So, but now we have 4, but they're not all palindromes, right? Let me see how many people have submitted this. So only 13 people have accepted this. This seems like it's going to be another very hard one, from what I can tell. Let's actually see what the other acceptance rates are. Yeah, so this, we get at 5.9 thousand versus 13. Okay, so yeah, the difficulties here are getting kind of crazy. Okay, so what we could do, so we could change this, right, to 0. I feel like there's a greedy solution here, but I'm just having trouble pinpointing it exactly. So here, we could say 0, we change it to 0, so now we have, this is a palindrome, like this column is a palindrome, right, 0, 1, 0. This row is a palindrome, but we have 4. We have this is not a palindrome, this is not a palindrome. So what we can do is we have to say, now change this to 0, this to 1, right? So now this becomes a palindrome, this becomes a palindrome, but now we have 1, 2, 3, 4. So we still have 4, but now we have to change this, right? So we could change this to a 1, but then we'd have 1, 2, 3, 4, 5, right? So that's not going to work. So I'm trying to think of just like a greedy solution here. So it seems like the what if we change? Let me try a different case. Let's try this. I want to try to make this as non-palindromic as possible, right? So none of these rows or columns are palindromes currently. So how do we figure this out? Well, we can change take this I'm just thinking right now for the best way to approach this. So we need to have a number of ones mod 4 equals 0, right? So how do we do this? Well, obviously it has to be mod 4, or the number of ones can be 0, right? So I think in this case it's either like we need to make it so that either we can have 4 ones and they're palindromes, right? So in the 3x3, can we do this, right? Well, the only way to do this is that they're all at the corners, essentially. So um, let's see. So we could, is that what we want to do? Try to get like the ones on the corners. So what if we had something, what if we had a 4x4? If we had 1, 0, 0, 1. We had 0, 0, 0, 0. We had, let's put the 1 here, and then we'll have 0, 0, 0, 1. Right, so what we could do here is we could change this to 0 and this to 1. Well, what if we had more than 4 ones? What would be the best way to do that? So what if we had just another random 1 here? Right, so it might still be to change this to a 0, change this to a 0, and change this to 1, right? So here in 3 moves, so like to get the corners, and what if we had 8? What would that look like? How could we arrange this so that we had 8 ones, right? So we'd have to have 1. I don't think that's possible. We'd have to have these corners here, or then 0, 1. So probably something like this, 0, 1, 1, 1, 1. Right. I think that's the only way we can make these all palindromes, and this becomes 0. So this is the only way I think that this could work, right? So I feel like a pattern we can kind of pick up from this. Right, so uh, so what if we scattered these around, right? What if we put this one here and we like got rid of this one, made it a 0? Okay, so we have 1, 2, 3, 4, 5, 6, 7. Right, so either we can remove 3 ones potentially and then rearrange the rest, or we can add 1 and then rearrange. So we need to do maybe like 2 steps. We have to do 1, add or remove, and 2, rearrange, right? So, and I think with 4 ones, there's 2 configurations. You can either do all the corners, or another valid configuration of ones would be if we did just the middles here, and then everything else was zeros, right? So I'm thinking like, is there a dynamic programming approach or like something, because the constraints are pretty high, so I don't think we can do something like backtracking. There must be just some sort of algorithm to figure this out. But I'm not sure what that is. Like, is it greedy? Or are we trying to, like, what do we know about palindromes? They have to be the same front to back, and back to front, right? So what if we were to, like, start at a certain position here and say, is this a palindrome? Well, technically, yes, you see the same back and forward. So I think here we could move on to this smaller subproblem and say, is this a palindrome? Right here. Well, no, that's not the palindrome. Is this. Okay. Um, right. So if we're looking at a row and column, say this row and this column, we know that definitely these three. So this, and this all have to be the same, right? Because for these to both be palindromes simultaneously, those have to be the same element, right? So we know that the corners must be the same. So corners be the corners must be the same, right? So that's one thing we know for sure. So all these corners have to be the same. Then we know that all of these. So then for the columns, we know that the top and bottom must be the same, right? And then can we work our way inwards then? Like this is our entire matrix here. But then once we determine that like all this is the same, we can then go into this submatrix here and say like what's the number of steps to make this a palindrome? Um, Maybe that would work, but then we still have to think of the number of ones, right? And make sure this mod 4 equals 0. The total number of ones in the grid is divisible by 0. Okay. Um, Look at Q4. Maybe it'll be easier. There's an undirected tree with n nodes. Oh, this only has 13 submissions. Okay. You're given a 2D integer array edges of length n-1 where edges u are tree. If I is odd, then x. Alright, these both seem like pretty tricky problems. Um, hmm. So maybe like kind of divide and conquer or like recursive where we're checking are the corners the same, are the columns the same, right? And then, so what if they aren't the same? What if we had a 1 here, right? Here we know that if, here we have 5 ones, right? So we have 5 ones. Here we know that we can just get rid of this if we want to, right? So say these don't match. If we have 5, right? So we can either get rid of a 1 to make it 4, or overall we have to add 3 ones to make this all the same, right? So I'm trying to think during each step, is there kind of a way we can use this logic and say, how many ones do we have? What's the optimal choice to make here? Should we remove one? The thing is, like, if we remove one, we don't know if when we get into this inner, if we're going to have enough ones, right? So, say this was 0. What if we had something like this, where we had 1, 1. So let's say this. We have 6 ones. Let's say, okay, let's remove. We have 5 ones out there. Let's say this middle one. This is a 0. So we have 1, 2. This looks like a 1. This. So we have 1, 2, 3, 4, 5. So we can say, all right. So we need to make all of these equal. So what we can do is say we will either remove, right? You can remove at this point at most 1, 1. So we actually can't remove a 1. Well, actually we can, right? So we could remove these 2 and we'd have 3, and then we would add this 1 in here, right? So it seems like our choices are dependent on the choices we make previously. This is hard. This should definitely be a hard problem. This is like kind of crazy. Um, let's see. And the minimum number of cells that need to be flipped. Forward and backwards. So, like, would there ever be a situation where we want to, like, say we have 3 ones? Would we ever want to go to 8? I mean, I don't think so. Like, it always makes more sense to go to 4 and then rearrange them, right? So we should always try, maybe try 2 choices. Like, we remove ones until we get to that, um, until we get to a number divisible by 4, and then we rearrange them. So what would that look like? So we would just say, let's remove our random one. Let's remove this one, right? So now we have 4. So what does this look like? So now at this point we know to actually like move a 1. Like to move, we actually have to like flip 2. So we can say this becomes 0. We want to move this up here, right? Like if we want to get this, we'd have to go here. So, but is that the right choice, right? Because what if, for example, we had this 1, 2, 3, 4, and this was 0. Let's use a smaller example. Let's use the example from before. So we'll have 1, 0, 0. We have 0, 1, 0, and then we have 0, 0, 1, right? So here we can either go to 0 or go to 4. Let's prioritize going to 4 just because we know that that's the answer. We can see it, but also because 3 is closer to 4 than 0, right? So, let's see. So now we can say, all right, so we need to add a 1. We could just maybe add it in any random place. What if we were to add it here, right? So now that means we've taken 1 move. So at this point, what we need to do is then we need to move some things around, right? So we basically can then flip this and this. This becomes 0 and this becomes 1. So that's 3, but then we also have to do this and this, right? So 0, 1. So then we actually got 5 moves there. So maybe we can't just place them arbitrarily. We have to like intelligently decide And maybe we do that with our corners, right? So if we have to add, right? So if we have to add ones, let's put that back where it was, 0 and 1. So here we know that we need to add a 1, right, to get to 4. So let's look at our corners and we'll see what's the difference, right? So here we know that we have to add a 1, and we know that our corners need to be the same. So if we cross this out and put a 1 here, that means essentially that we now have done one move, and then we can move this to here, and that's 3, and this is a palindrome. So if we're adding ones, then we want to um, add it to the corners, maybe? Like, because we know that all the corners have to be the same. So if we have to add, and the number of ones in our corners is greater than the number of zeros or equal, then we should add a 1 there. Because that's free, right? We're switching one bit and adding a 1 rather than rearranging. But what if we had something like this? What if we instead had this here, right? So here what we'd have to do is we could say we need to get to 4, right? So we can again do this here, and then yeah, it's the same thing. So maybe we have to move away from the corner situation. So what if we did this? And then we said, okay, so we need to add a 1. But we look and we see that we only have 1 in the corner. So we know that if we added 1 to the corner, we still have to do other moves to get this to be a palindrome. So what we could do is add 1 to this is a palindrome, but then we have to make basically every other row is still not a palindrome. So this would be a palindrome, this would be a palindrome. We need to update this, update this, update this, update this. Or in this case, we could, right, so that's the only way in this to have 4, and it could be a palindrome, right? We know that they have to be in the corners. So in a 3x3 matrix, I think that's the only configuration where we could have 4. They have to be in the corners. I'm trying to think of another situation. So we have 1, 1. What if we had like 1, 1, 1, 1? Actually, we could do it this way. Do like 1, 1, 1, 1, 1, 0. So you could also do it this way. Okay. But checking all the ones seems very, like it just doesn't seem practical, right? Like how do we compare, how do we know that we're doing it in the optimal way? Um, so like when this is kind of a base case, I'm thinking like when we have a 3x3 grid and we have 4, there's basically 2 configurations, either the corners or this kind of diamond shape, right? I can't really think of any other case that we could have. So if we treat this as a base case, we say if we have a 3x3 grid, it has to be one of these. So what's the minimum to get to one of these states? And then like maybe from there, if we have a larger matrix, we kind of like expand out and say, okay, so when we have one of these, but then we have to keep track of the state, right? So we need to know which one we updated it to. Geez, what a mess. What a mess. Okay. Move on to Q4 for a bit, see if we can get this. Actually, all nodes are unmarked. For each node, if I is odd, the node will get marked at time x if there is at least one adjacent node adjacent to it, which was marked at time x minus 1. If I is even, they'll get marked at time x if there is at least one adjacent node x, which was marked at x minus 2. Okay. Then, turn array times, or times I is the time when all nodes are marked in the tree. If you mark node I t equals 0, when you mark times I, all nodes are unmarked. But that each answer for times I equals 0. Okay, so return array time for times I is a time when all nodes get marked in a tree if you mark node I at time t equals 0. So for I equals 0, node 1 is marked at t equals 1, and node t equals 2. When all, oh I see, so we're starting at 0. Mark node I at time t equals 0. So we're marking this here. We're basically saying, okay, so we'll go to node 1. This got marked at it's time 1. And the adjacent node was marked most previously at 0, right? So we could say, all right, so we saw that this got marked here. When we go here, we say that this has to get marked at time equals 2, right? So 0, 2. So if I equals 1, right, it's even, so this has to get marked at 2, right? And then this has to get marked at 2. Okay, so here I'm thinking like, we start a breadth first search. I'm trying to think if there's some other way to do this of like, breadth first search might be too slow. Like I'm thinking we start a breadth first search at each node essentially. But I think that's basically n squared, right? Which I think will be too slow. Like for example, we'd have to start at 1, go through every other edge, then start at 0, go through every other edge too. Right, so I think that's going to be inefficient as well. So maybe there's just some algorithm here. I just like Bellman Ford or something. Which I don't really know. So compute shortest paths from a single source vertex to all the vertexes in a weighted graph. Shortest path, Floyd Warshall maybe. So find the shortest path between all pairs of nodes in a weighted graph. But is this weighted? Kind of, maybe, because you can kind of think of it as like, this has a cost of 1, maybe, because going from 1 to 0, because this has to wait for 2. Like the edge, if you're thinking of it as 0, right, the cost to get here or to have this adjacent node mark here is 2, right? Because whatever this time is, we have to add 2 onto that. So we can maybe like do it that way. Like if even then it costs from all my other things, but I just don't even know how to write this algorithm, so I don't think I'm gonna try to write this during a competition. All right, let's go back to Q3. Still insanely low, 500 accepted with 7.1 submissions. It's like these Q3s are getting like insanely hard. Flip any number of cells. Okay, so let's think for a 3x3 grid. How would we actually go about doing this? So say we have, let's go back to the original configuration, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Right, so programmatically, how do we figure out if this is a palindrome, right? So we already established that the corners all have to be the same, right? This will be for a matrix of any size, they have to be the same, because otherwise they're not a palindrome. Like here, if these don't match up, if 1 doesn't equal 0, there's no way this row can be a palindrome. Likewise here, if this doesn't match this, it can't be a palindrome. So we know that the corners have to be the same. Other than that, what can we do? So they can either all be 1s or they can all be 0s. So is there a way to then determine from there? So we maybe find the minimum number it takes to get all here, but then we have to worry about these inner ones as well, right? Is this inner column a 0? Is this inner row a palindrome? Like, I almost want to think this is like dynamic programming, but the constraints are too high. I don't think we would just time out. I don't think there's any way to really do it with DP. Let's see. So 1, 1. Okay, so maybe. So I think 1. I think this is solid. So we either need to go up or down to closest 4. But maybe closest isn't the right way to think about this, right? Because if we have a bunch of 1s like here, so what if we had 1, 1, 1, 0, 0, right? So technically these are all palindromes, but to actually get these 1s to their respective positions, we'd have to do 2 to get this here, 2 to get this here, 2 to get this here, and then we can just do 1 move here. So that's actually 2, 4, 6, 7, right, to do that. So maybe we need to know what it's actually cheaper to just get rid of all the 1s to make this a palindrome. So it would be 3, 4, 7. So obviously we want 3. So maybe we need to like know the closest palindrome. And what I mean by closest is, right, like what are we looking for? What, with a grid of a given size, how do we, like, what's the closest palindrome that we can make, right? And how do we figure that out? So here we know that this is already palindromic, but we have to have 4. If we have to have 4, that severely limits the number of configurations that we can have, right? And as we said before, for a grid of 3 by 3, we could either have only the corners be 1, or we could have these being 1, right? So actually what we could do to get all these 1s is we say get rid of this, 2, 3, right? So actually that's a palindrome. So this way we could also do 3. So 3 or 3, doesn't matter. Okay, so get rid of that, and then add a 1 there. Okay, so we'll see that depending on how this is laid out, let's do a configuration where they're kind of just like scattered. What if we had 1, 0, 1? Let's do 0 actually. 1, 0, 0. We have 1, 0, 1, and then we'll have 0, 0, 1. Right, so what we could do, there's 2 ways to get this working. We either cross these 2 out, and then we get 1, 1 here. So it'd be like, these 2 become 0 in 2 moves, and then these 2 become 1 in 2 moves. 4. Otherwise, what we could do is say, for here, I could cross this one out and this one out, and then I make these, right? So I guess it's like the number of 1s in proper places, right? The number of 1s in proper places. Okay, so we have like 2 in the proper place and then 2 in the proper place here. And then basically we have to add that plus the number of other 1s, right? So we have 2, but then what we can do is say, wait, no, is that 2? So we have these 2 here, 1, 2, 3, 4, right? So we have 2 in the proper place, and then the number in wrong place, right? So this would equal 4. So we have 2 in the right place here, and we can look at this either way. We can either treat this as the right place or these as the right place. So we have 2 plus 2 in the wrong place equals 4. But what if we didn't have this 1, right? What if we have this 0? So here we have 2 in the right place, and then we could do add 1 here. So this is 1, oops, hold on. This is 1 move, and then we have 2, just 3 moves overall. Okay. So here they're just making it seem like it's the number of 1s, which I know it is not. Like all of these answers they're providing are just the number of 1s in the grid, which can't be right. I think that's kind of a trick that they're putting forward. Okay, so we kind of know what to do for a 3 by 3 grid, but what if we had 4 by 4? What if we had 0, 1, 0, 1, 0, 0, 1, 0, and we had, remember this is also m by n, so potentially, let's actually think of that case. What if we had a 3 by 2 grid? 3 by 2. So what if we had 0, 1, 1, 0, and we had 0, 0. What do we do here? Right, so this is a palindrome. So what we could do is either say I want to move this here. Right, I want to get rid of this 1, make this a 1, right? So we could do that in 2 moves, or we could just get rid of all the 1s and make them 0s and also do that in 2 moves. So I'm thinking maybe if we have less than if we have less than 4 1s, just remove. Right, we could either have to add a 1. Well, no, because there is a situation if we had something like this, 1 0 0 0 0 0. We had 1 0 1. Right here, we can just do this in 1 move. Um, so this is not always the case, right? This is not always the case. Maybe in some cases, but I think in this case, not quite. Um, this is quite difficult. Yeah, this should 100% be a hard problem. I'm pretty convinced. Uh, to make all rows and columns palindromic, the total number of ones in grid divisible by 4. Let's see. Okay, so we maybe don't think of moving. Of moving ones, right? Just think of deleting, oops, deleting, refresh the page. How annoying. Deleting and adding. deleting or adding. Right, so how do we determine what is optimal? Okay. I'm just going to play with this test case until I can figure out some sort of algorithm here. Because, like, the constraints are high, right? The constraints are 2 times 10 to the 5 for m times n, right? So it's a fairly large grid. So it can't be any sort of, like, brute force algorithm. It must be something greedy or just some observation that I'm not having currently. Um, so here we could say is what makes a palindrome, right? So we could either have 4, like how many configurations are there to make a palindrome in this case, right? Like how, there's 2 ways. 2 ways we can have palindrome before, but, and then 1 way for, with 8, can we do it? I don't believe so. I don't think anybody would do this with 8. Yeah, I can't. 1, 2, 3, 2, 3. Yeah, I think we could do just these 2 ways, right? I don't think there's any other way, or we could do 1 way with 0, right? So I guess the question is, how do we say say we find the minimum for this, right, of these 2 ways. Either one of the 2 ways before, and then we return that back up to the larger matrix. But that doesn't account for our other case where we have something like this. We have 0, 1, we have 0, 1, and we have 0, 0, right? So for this case, that doesn't really match, right? Because if we have all these being corners, I guess technically it's a palindrome. Like if we had 1, 1, 0, 0, 1, 1, that's valid, but that's not exactly the optimal case here. So do we have to go like row by row and say, is this a palindrome? If not, how many do we have to change to make it a palindrome? So say here, we could say, I have to, if I want to make the palindrome, change at least one of these, right? So it would be the minimum of removing this 1, right? So remove 1, or add that 1 here, right? So we basically have to go through the row, check if it's a palindrome, and then at each step either add or remove a 1. But this has implications for future states, right? We don't know if the choice we make right here is going to affect later options. So I don't think we should just greedily choose this. We'd have to do some sort of dynamic programming, but that also involves keeping track of the states at each iteration. There's going to be way too much memory because we're doing this for an n by n grid, right? So I don't think realistically we can do DP here. I think there is just some greedy algorithm that I cannot figure out at the moment. God, look at this. Look how low this is. Let's do the 1.1. divided by 13. That's 6. Yeah, this times 8. So about 8%. That's pretty insane. They are really... divided by 400. So it has to be greedy, right? Or there has to be some observation because we've confirmed that we cannot do DP. So it's greedy or some observation, right? So when we have less than 2, like if we have 2, just remove them, right? That's easier. If we have 3, then it depends. Like we could either add 1 and then try to rearrange, or we could just remove the 3. Right, so let's say, let me try to actually write some code here. So let's say number of ones equals 0 for row and grid for L in row if L equals 1. Okay, right, so now we know the number of ones. So we'll say if the number of ones is less than or equal to 2, return the number of ones, right? Because we're just going to remove them. Just remove ones. Let's make sure I look at the constraints, see if there's anything that we missed, right? So no, no, no. Okay, so sometimes the constraints have some valuable things, but not in this case. So otherwise, we have to actually figure out what is the best way to do this, right? So either we want to add ones till we get to the next divisible by 4 value, but we've seen that it matters where we add them, right? So we can't just blindly add any. We need to make sure that we're doing this in like an intelligent way. Okay, so let's see what I get here. Let's return 0. So I should pass these 2 test cases, right? So here I get 2, here I also get 2. Okay, so this handles the case where we just have less than or equal to 2 ones, which is a pretty rare case, so we shouldn't run into this that much, but then we need to handle all these other cases. So what if we had 3 here? We still need to figure out how to rearrange them. So if a column has, if we had 3, um, we could either add. So here, I don't think there's any way we could actually have a palindrome unless we had these four corners set, right? So it has to be the corners. Always has to be the corners. Or we can, right? That's the only way. What if we had like a 1 by, we had 1 0 0 1. Okay, so in this case, we have these corners, but the only other way we could have 4 is if we have this middle section here. What if we had 5 by 5? So we had 1 0 0 0 1. We had 0 0 0 0 0. It'd be tedious to write this out. These should be 1s here. Should be 1 1. Right, so here, how can we have 4? We could have, say, like here, 1 2 3 4. Again, our corners, right? And then how could we have another 4? We could have these 1 2 3 4. 1 2 3 4. It's hard to tell. So we have like basically all these ones here, all these ones here. But we could also have another 4. 1 second. We have 0 0 0 0 0 0 0 0. We can also have 1 1 1 1 1 1 1. We could also have this. Okay. And then how do we do another 4? It would have to be 1 2 3 4. Alright, so we could do 1 2 3 4 here. 1 2 3 4. Alright, I'm going to call it quits here. I don't think I'm going to be able to solve this here, but we'll post a follow-up video showing everyone how to solve this once I figure it out. So hopefully you enjoyed this. Thank you for watching.